26 April 1986, 0123, Unit 4 Control Room, Chernobyl Nuclear Power Plant, Ukrainian SSR. In the logbooks, the reactor reads 200 megawatts, 6% of full power. Automatic protections disabled for a turbine test leave the core dependent on human judgment. At 012340, operators press the AZ-5 emergency shutdown button. They expect the reactor to stop. Instead, power surges toward tens of gigawatts in seconds. 2 explosions destroy the core and building. Within minutes, radiation near the exposed reactor measures 5.6 roentgens per second, 20,000 roentgens per hour, enough to deliver a lethal dose in under 2 minutes. The test designed to improve safety would redefine it. From this single button press, minute by minute, a sequence unfolded that changed nuclear policy worldwide. This is that story. A technical manual for the RBMK 1000 lies open on a control room desk in early 1986. The diagrams show 1,661 pressure tubes arranged in a graphite moderator block, fed by light water coolant, driving dual 500 megawatt turbines. The reactor type is described in Soviet documentation as a graphite moderated pressure tube type reactor, using slightly enriched uranium dioxide fuel, intended for both power generation and plutonium production. The Design Bureau presents the RBMK 1000 as flexible, powerful, and capable of load following. Official brochures describe Chernobyl as a flagship of Soviet nuclear power, supplying electricity and district heat across the Ukrainian SSR. The design carries specific characteristics. Graphite acts as the moderator, slowing neutrons to sustain fission. Light water cools the fuel and removes heat, but also absorbs neutrons. When water boils to steam, fewer neutrons are absorbed. In an RBMK, this increases reactivity, a positive steam void coefficient. Most Western reactors have negative coefficients. More steam means less reactivity. The RBMK behaves oppositely within certain regimes. Control rods manage reactivity. Each rod consists of a boron carbide absorber section with graphite displacers above and below, separated by water-filled gaps of 1.25 meters. When rods are fully withdrawn, the graphite displacers sit in the active core zone, replacing water. On insertion, water briefly re-enters before boron arrives. In normal operations, this sequence causes no issue. At low power, with many rods withdrawn and high void fractions at the core bottom, the initial displacement of graphite by water can add reactivity before absorption dominates. Post-accident analyses identify this as the positive scram effect, an unintended consequence of rod geometry. The design assumes operation within prescribed envelopes. Operational reactivity margin, the number of effectively inserted control rods, must remain above minimum thresholds to ensure controllability. Power levels. Below 700 megawatts thermal are discouraged for extended periods. The combination of positive void coefficient, control rod design, and operational limits creates a reactor that behaves predictably within its licensed range. Outside that range, behavior becomes nonlinear and potentially unstable. Later international reviews, including the IAEA's INSAG-7 report, note that the RBMK had significant design deficiencies not fully understood by operators before 1986. Training materials acknowledge the void coefficient, but do not emphasize the combined effects at low power and low margin. The same features that made the RBMK economical and flexible also established conditions where, in a narrow band of operation, emergency protection could briefly worsen the situation it was meant to resolve. 25 April 1986 begins as a routine day at Chernobyl. Unit 4 operates at full power. In Pripyat, 49,000 residents go about daily life. Ambient radiation levels in town remain near natural background, roughly 0.1 microsievert per hour. The morning shift expects a standard workday. A test program, stamped and approved, sits in the control room. The objective? Verify that the turbine generator, during coast down after a grid disconnect, can supply power to the main circulation pumps for 40 to 70 seconds, the gap before emergency diesel generators reach full capacity. The test has been conducted successfully on other RBMK units in 1982 and 1984. The written plan assumes execution during daytime hours with experienced personnel, stable reactor power between 700 and 1000 megawatts thermal, and all standard protections available. Grid dispatchers, managing electricity demand across the region, request that Unit 4 remain at 50% power longer than originally scheduled. The request is routine, balancing supply and demand. The consequence, however, is not. The delay pushes the test from day shift into evening and then into the night shift. Staffing changes. Alexander Akimov, the shift supervisor, and Leonid Toptunov, the senior reactor control engineer, take over. Both are competent, but Toptunov has been independently certified on the RBMK for only months. Anatoly Dyatlov, the deputy chief engineer overseeing the test, remains present but does not operate the controls himself. The test protocol includes one early step: manually isolate the emergency core cooling system to prevent it from automatically injecting water and interfering with measurements. The valves are closed. The system is designed to provide emergency coolant if normal circulation fails. With ECCS isolated, that protection is unavailable. The written procedure states the test should be completed quickly. In practice, the ECCS remains isolated for roughly 11 hours, far longer than planned, as the grid delay extends the timeline. No single decision appears reckless. In isolation, grid operators request extended generation. Managers approve the delay. The night shift takes over with a valid test plan in hand. ECCS isolation follows the written steps. Each action fits within standard operational flexibility. Together, however, they alter the context. Less experienced operators, circadian fatigue, compressed time to complete the test before the next scheduled shutdown, and a major safety system unavailable for an extended period. By the time the night shift fully assumes control around midnight, the test program remains unchanged on paper. Almost every assumption behind it, timing, staffing, system availability, has been quietly invalidated. Late on 25 April, the night shift begins reducing reactor power. The plan calls for stabilization near 700 megawatts thermal, a level providing adequate flow, controllable xenon, and sufficient operational margin. Control room instrumentation records the descent. Power passes through 1000 megawatts, then through the 700 megawatt target band. At approximately 0030 on 26 April, power drops sharply and unexpectedly to roughly 30 megawatts thermal. The cause is multifaceted. Xenon-135, a fission product with an enormous neutron absorption cross-section, builds up during reactor operation from the decay of iodine-135. At high power, xenon is burned away by neutron flux. At reduced power, production from iodine decay continues while burnout decreases. The reactor enters xenon poisoning, a condition where accumulated xenon absorbs neutrons faster than fission can sustain the chain reaction. Additionally, control actions during the power reduction may have been imprecise, compounding the drop. 30 megawatts is far below the planned test range and well outside recommended RBMK operating envelopes. Dyatlov, under time pressure to complete the test before dawn and the scheduled maintenance shutdown, instructs the operators to recover power. The only tool available is withdrawing control rods to add reactivity and overcome xenon poisoning. Akimov and Toptunov comply. Rods are withdrawn progressively. Power begins to climb, slowly at first. By approximately 0100, the reactor stabilizes near 200 megawatts thermal, within the minimum acceptable range for the test, but still far from the intended 700 megawatts. The recovery comes at a cost. Operational reactivity margin, the number of control rods effectively inserted, falls to critically low levels. Operating procedures specify a minimum ORM to ensure the reactor remains controllable under all conditions. Post-accident reconstructions indicate that, by the time power stabilizes at 200 megawatts, only 6 to 8 rods are effectively inserted, well below the minimum of 15 specified in guidance, and possibly as low as the absolute operational limit of 30 equivalent rods required by regulations. Low ORM places the reactor in a state where small changes in coolant conditions produce large swings in reactivity. With many rods withdrawn, the core's reactivity margin, its cushion against perturbations, is nearly exhausted. The RBMK's positive void coefficient now dominates behavior. Any increase in steam formation will sharply increase power. Any decrease in coolant flow will increase voids. Technically, 200 megawatts falls within the test band specified in the program. Practically, the reactor is in a configuration never analyzed in the original safety documents. The numbers on the control panels, power output, coolant flow, pressure, appear acceptable. The hidden variables, ORM and rod distribution, tell a different story. Between 0028 and 0105 on 26 April, operators prepare the reactor for the test. Alarm lamps illuminate on control panels as systems are taken out of automatic mode. The actions are deliberate, following perceived test requirements, not sudden or panicked. The local automatic regulation system, which adjusts control rods to maintain stable power, is disabled. Operators will manage power manually during the test. Several reactor scram signals, automatic trips designed to shut down the reactor when parameters exceed limits, are bypassed or inhibited. The logic: prevent an automatic shutdown from aborting the test. If pump flow, power distribution, or other monitored values drift outside normal bands during turbine coast down, the emergency core cooling system remains manually isolated from earlier. Additional main circulation pumps are brought online, increasing the total number of running pumps beyond normal operating configurations. More pumps mean higher coolant flow, which reduces steam voids and reactivity. To maintain 200 megawatts with increased flow, operators must withdraw additional control rods, further reducing ORM. Each protection bypass appears justifiable in context. The test requires a brief transient, 40 to 70 seconds of turbine coast down. Automatic systems, not understanding the test is underway, might interpret changing conditions as faults and trip the reactor prematurely. Disabling certain interlocks is framed as necessary to complete a sanctioned experiment. No single switch throw is obviously catastrophic. Collectively, however, the sequence dismantles defense in depth. Modern reactor safety philosophy layers multiple independent barriers between operators and catastrophic outcomes: physical barriers, active safety systems, passive design features, and automatic protection logic. At Unit 4, as the test approaches, most automatic protections are offline. The ECCS, normally a last resort if cooling fails, is unavailable. Scram signals that would halt the experiment are inhibited. The reactor's safety now depends primarily on the operator's ability to recognize dangerous conditions and manually intervene in time. On the control panels, individual lamps indicate which protections are bypassed. Each lamp is small. The panels provide no single integrated display summarizing system safety status. The combined meaning that an RBMK temporarily relies on human judgment rather than engineered safety systems is not captured in any annunciator or alarm. Later reviews note this as a deficiency in human-machine interface design. Operators focus on individual parameters: power level, coolant flow, pump status. The overall safety posture of the reactor, degraded by cumulative bypasses, remains difficult to perceive from the available indications. By 0105, Unit 4 is technically ready for the turbine rundown test. Power is stable at 200 megawatts. Pumps are running. Protections are bypassed as deemed necessary. The configuration exists nowhere in the design basis or safety analysis. The test is about to begin. A training diagram in an RBMK classroom shows reactivity feedback curves: fuel temperature, moderator temperature, coolant void fraction. Most shift operators see simplified versions during certification. The full implications of combining these feedbacks at extreme low power, low ORM, and high void fraction are not widely understood in 1986. Design documentation acknowledges the RBMK's positive steam void coefficient. When water boils to steam, neutron absorption by the coolant decreases, reactivity increases, and power rises. This feedback is manageable within the reactor's intended operating envelope: high power, adequate ORM, controlled void distribution. Designers calculate void coefficient magnitude and incorporate it into safety analyses. Operators are told the reactor is stable when operated according to procedures. What is less emphasized? At low power with many control rods withdrawn, the positive void coefficient can dominate all other feedbacks. Small increases in steam formation from reduced coolant flow or local hotspots can trigger large, rapid power increases. The reactor's ability to self-regulate diminishes as ORM decreases. Control rod design adds a second, subtler issue. Each rod has a boron carbide absorber for neutron absorption, but graphite displacers occupy much of the rod length to reduce hydraulic drag and improve displacement efficiency. When rods are fully withdrawn, these graphite displacers sit in the lower part of the active core, replacing water that would otherwise absorb neutrons. Water-filled gaps of 1.25 meters separate the graphite sections from the boron sections. When AZ5, the emergency scram button, is pressed, all rods begin inserting at approximately 0.4 meters per second. Full insertion takes 18 to 20 seconds. During the first seconds of insertion, the graphite displacers move downward, temporarily displacing water at the bottom of the core with graphite. Since graphite moderates neutrons better than water, but does not absorb them, this displacement briefly increases reactivity in the lower core region before the boron sections enter and begin absorbing neutrons. Under normal conditions, adequate ORM, moderate power, distributed rod positions, this transient effect is negligible. Boron absorption quickly dominates, and power drops as intended. At low ORM with rods nearly fully withdrawn, especially with high void fractions at the core bottom, the initial insertion can produce a localized reactivity spike. For a few seconds, the emergency protection system adds reactivity instead of removing it. Designers knew the effect existed, but underestimated its significance in certain low-probability operating regimes. Post-accident analyses from multiple international bodies confirm this positive scram phenomenon as a critical design flaw. INSAG 7 and subsequent reviews note that operators were not informed of the risk. The AZ5 button, labeled and understood as the ultimate safety measure, carried a hidden conditional behavior. In the wrong state, pressing it could briefly worsen an excursion before eventually terminating it, if the reactor structure survived the first seconds. At Unit 4 on 26 April, the wrong state is precisely where the reactor sits, 0105 to 0123. Operators monitor instruments as the final test preparations continue. Power holds near 200 megawatts. Coolant flow is elevated from the additional pumps running. Inlet temperature to the core is slightly lower than normal due to the increased flow rate, which reduces subcooling margin and affects void formation patterns. The test program specifies that 4 main circulation pumps should be powered by the coasting turbine generator, demonstrating that generator inertia can sustain coolant flow during the brief gap before diesel generators come online. Each pump requires approximately 5.5 megawatts of electrical power. With the reactor at low thermal output, the electrical balance is delicate. Pumps consume a significant fraction of generator output. Adjusting pump configuration affects the reactor. Starting more pumps increases flow, which collapses steam voids and reduces reactivity. To maintain 200 megawatts, operators withdraw more control rods. This further erodes ORM. Conversely, when the turbine trips and the generator begins coasting down, pump power will decay. Flow will decrease. Voids will increase. Reactivity will rise. In a reactor with adequate ORM, control systems and scram protections can manage this transient. At Unit 4, with ORM below limits and protections bypassed, the margin for error is narrow. Reconstructed timelines show multiple pump starts and configuration changes in the hour before the test. Each adjustment is an attempt to stabilize power and flow. Each compounds the low ORM condition. Operators are focused on maintaining the 200 megawatt power level required for the test. They monitor flow rates, temperatures, and pressures. The control panel does not display ORM directly as a single prominent number. Calculating ORM requires summing the effective worth of all inserted rods and comparing it to minimum limits, a task not easily done in real time during a dynamic transient. By 0120, the reactor appears stable. Power output is steady. Coolant temperatures are within acceptable ranges. No major alarms are sounding. Most protective trips have been intentionally disabled. Turbine parameters are nominal. From the operator's perspective, the reactor is ready for the test. From a safety analysis perspective, The reactor is in a configuration that would not be licensed. Low ORM, positive void coefficient dominant, protections offline, operating in a low-power regime where small perturbations can cause large effects. The test program is about to answer an engineering question. Can the turbine generator's rotational inertia provide temporary power to pumps during a station blackout? The program does not anticipate answering a far more consequential question. What happens when an RBMK at low power, low ORM, and high void coefficient receives a reactivity insertion from control rod movement? As the clock moves past 0123, the test begins. For the next 40 seconds, every reading, every mechanical action, every neutronic feedback will interact to determine whether Chernobyl Unit 4 continues operating or becomes the worst civil nuclear accident in history. 012304. An operator closes the turbine stop valves. Steam flow to the turbine ceases. The generator, no longer receiving energy input, begins to coast down. Rotational speed falls from nominal. Generator frequency decays. Electrical output drops. The test plan anticipates a predictable coast-down curve based on turbine generator inertia. Engineers have calculated how long the spinning mass can supply power to the main circulation pumps. The expectation, 40 to 70 seconds of adequate pump power before diesels reach full output. During this interval, coolant flow should remain sufficient to remove decay heat and prevent core damage. Reality diverges from expectation within seconds. As generator output decays, pump power decreases faster than optimal predictions. 4 main circulation pumps, each drawing roughly 5.5 megawatts, lose power gradually but steadily. Coolant flow into the reactor core begins to fall. Less flow means less heat removal. Coolant temperature rises. Boiling increases. Steam voids grow, particularly in the hotter regions at the top and middle of the core. In an RBMK with a large positive void coefficient and nearly depleted ORM, increasing voids directly increases reactivity. More voids mean fewer neutrons absorbed by water. Fission rate increases. Power begins to rise. Instrumentation in the control room shows power climbing from 200 megawatts. Operators observe the increase, but initially interpret it as within expected. Transient behavior during the test. Seconds matter. Power continues to rise. The reactor is now in a feedback loop. Reduced flow increases voids. Increased voids increase reactivity. Increased reactivity increases power. Increased power generates more heat and more voids. The loop accelerates. With adequate ORM and automatic scram protections active, this transient would trigger a shutdown. Control rods would insert. Power would drop before reaching dangerous levels. At Unit 4, protections are inhibited. ORM is minimal. The reactor drifts toward instability with no automatic barrier intervening. Reconstructed power histories based on post-accident forensic analysis of instrumentation traces and physical evidence show power rising through the expected range within 10 to 15 seconds of the turbine trip. Operators see the trend. Procedures call for monitoring, not immediate manual scram, during the test window. The test is supposed to last 40 to 70 seconds. Events are now moving faster than procedural guidance anticipates. By approximately 0123:35, roughly 31 seconds after turbine trip, power is climbing more steeply. Void formation is accelerating. Local power densities in certain fuel channels are increasing rapidly. The reactor is entering a regime where neutronics, thermal hydraulics, and mechanical stresses begin to interact unpredictably. Control room indicators may not yet show the full severity. Some sensors have limited range, recorders have finite response times. The reactor core itself is changing state faster than the monitoring system can fully capture. By 0123:40, someone, reports vary on exactly who, presses the AZ-5 emergency scram button. All control rods are commanded to insert. The action is taken to terminate the test and shut down the reactor. It is the correct procedural response to an unexpected power increase. Under normal conditions, it would succeed. Under the conditions at Unit 4, it triggers catastrophe. AZ-5 activation sends electrical signals to control rod drive mechanisms across the reactor. Drives energize. Rods begin to move downward at approximately 0.4 meters per second. The first few centimeters of travel bring graphite displacers into the lower core region, temporarily displacing water. In fuel channels at the bottom and outer edges of the core, regions with higher void fractions and lower neutron flux, the replacement of water by graphite reduces neutron absorption before boron arrives. Local reactivity increases. Power in those channels spikes. Coolant in the affected channels flashes instantly to steam. Pressure rises. Fuel cladding ruptures. Some fuel assemblies may fragment. Water hammer effects. Sudden pressure pulses from rapid boiling. Stress pressure tubes. Several tubes rupture. The core geometry begins to deform. Power monitoring instruments record a surge. Within 3 seconds of AZ5 activation, power exceeds 530 megawatts and continues to rise exponentially. Neutron flux measurements reach instrument limits and saturate. Recorders cannot track the rate of increase. Post-accident analyses, reconstructing the sequence from physical damage patterns, witness testimonies, and instrument fragments, estimate peak power reached tens of gigawatts thermal, more than 10 times nominal full power, over a period of seconds. At such power levels, fuel temperature soars instantly. Uranium dioxide melts at approximately 2,800 degrees Celsius. Zirconium cladding reacts exothermically with steam above 1,200 degrees Celsius, releasing hydrogen and heat. Chemical energy adds to nuclear energy. Fuel pellets disintegrate. Coolant vaporizes. Pressure in fuel channels and the spaces around them exceeds design limits by orders of magnitude. At 01:23:44, approximately 4 seconds after AZ5, instrumentation begins to fail. At 01:23:48, a sharp jolt is felt throughout the building. The first explosion occurs. Evidence suggests a steam explosion, water flashing to vapor at extreme pressure, generating a shock wave. The explosion lifts the upper biological shield, a massive steel and concrete structure weighing approximately 2,000 tons, known informally as the reactor lid, displacing it vertically and rotating it partially. Pressure tubes shear, fuel assemblies are ejected, the core structure is destroyed. A second explosion follows within seconds, likely caused by hydrogen combustion or additional rapid steam generation as disrupted fuel contacts water. The building roof over Unit 4 ruptures. Debris, graphite blocks, fuel fragments, structural steel is ejected upward and outward. Some material lands on adjacent roofs. Graphite exposed to air and heated to extreme temperatures ignites. Multiple fires begin on the roofs of Units 3 and 4 and in the turbine hall. The reactor core is now open to the atmosphere. No containment building surrounds an RBMK. The reactor vault and building structure provide some shielding, but with the core destroyed and the roof breached, fission products and activated materials are directly exposed. Radiation fields near the reactor are immense. Early estimates, based on dosimetry and later forensic analysis, suggest localized fields near 5.6 roentgens per second. This is roughly 20,000 roentgens per hour, equivalent to about 200 Gray per hour. A 5 Gray whole-body dose is lethal to 50% of exposed individuals without medical intervention. At 200 Gray per hour, 5 Gray accumulates in 90 seconds. From button press to open core, less than 1 minute. The emergency protection system, the final safety barrier, has failed in its intended function. Emergency calls reach the plant fire brigade at approximately 01:24. The initial report: fire at Unit 4. Fire engines from the on-site brigade and the Pripyat fire station respond immediately. Lieutenant Volodymyr Pravik, watch commander of the Pripyat brigade, arrives with his crew within minutes. They see flames and smoke rising from the turbine hall and reactor building roof. What they are not told: the reactor is destroyed, the core is exposed, and radiation fields are extreme. Firefighting in 1986. Soviet Ukraine follows standard protocols for industrial and structural fires. Crews wear heat-resistant gear and self-contained breathing apparatus for smoke protection. Dosimetry is limited. Portable radiation survey meters accompany the brigades, but many saturate at high-dose rates, displaying maximum readings that do not convey the true field strength. No protective equipment exists that can shield against the gamma and beta radiation fields present near the destroyed core. Firefighters direct water streams onto burning roofs. Graphite blocks ejected from the core burn intensely on the roof of the turbine hall adjacent to Unit 3. Crews climb ladders and work on roof sections directly exposed to the open reactor. They are not informed of the severity. Some later testimonies recall being told the fire was from a hydrogen explosion in a turbine or auxiliary system. Serious, but within the realm of conventional industrial accidents. The concept that the reactor itself is destroyed and emitting lethal radiation is not communicated to frontline responders in the first hours. Dose reconstruction for firefighters and early responders varies by position and duration. Those working at ground level or inside the turbine hall receive elevated doses but may remain below thresholds for acute effects. Those on roofs near the reactor, especially the roof between Units 3 and 4, receive doses in the range of multiple sieverts over the course of hours. Vasily Ignatenko, Vladimir Pravik, Viktor Kibanok, and others accumulate doses later estimated between 4 and 16 Gray. At these levels, acute radiation syndrome is certain. Above 6 Gray, survival without bone marrow transplant is unlikely. By 0400, the main fires are largely extinguished. Graphite blocks continue to smoulder. Crews remain on site. Some responders already show symptoms: nausea, vomiting, headache, and a metallic taste, early signs of high-dose radiation exposure. They do not yet understand the cause. Contamination spreads through contact with radioactive debris and dust. Beta-emitting particles, fragments of fuel, activation products, fission products adhere to skin and clothing, causing localized high-dose exposures and beta burns. Official recognition of the disaster's radiological nature lags behind physical events. Plant management, struggling to assess damage in darkness with limited communication, initially underestimates severity. Some early reports state that the reactor is damaged, but largely intact. Visual inspection from ground level, obscured by smoke and darkness, does not immediately reveal the full extent of core destruction. Dosimeters reading off scale are sometimes dismissed as instrument malfunction rather than accurate indication of catastrophic release. By sunrise on 26 April, dozens of plant staff and firefighters have received doses that will define the medical and human narrative of Chernobyl for decades. Pravik, Kibanok, Ignatenko, and others will be evacuated to Moscow within days, treated at specialized clinics, and documented as some of the most severe acute radiation cases in medical literature. Of the approximately 134 individuals ultimately diagnosed with acute radiation syndrome from the accident, 28 will die within months, most of them firefighters and plant operators present in the first hours. The fires are controlled. The immediate emergency response, judged by conventional firefighting standards, is successful. Judged by radiological outcomes, it is a catastrophe born of misinformation and inadequate understanding of the situation these responders faced. 26 April, early morning. Ambulances begin transporting plant workers and firefighters to Pripyat Hospital, a small facility serving the closed city. Patients present with nausea, vomiting, dizziness, headache, and erythema, reddening of the skin. Initial medical assessments consider thermal burns, smoke inhalation, and chemical exposure. The pattern of symptoms, however, points towards something more serious. Physicians notice specific signs. Some patients exhibit severe vomiting within 1 to 2 hours of exposure, a hallmark of high-dose whole-body irradiation. Erythema appears in unusual distributions, faces, hands, and areas where contaminated dust settled. Some report a metallic taste and dry throat. Blood samples drawn over the first hours show precipitous drops in lymphocyte counts, white blood cells critical to immune function. Rapid lymphocyte depletion is a reliable indicator of significant radiation dose. By midday on 26 April, medical staff at Pripyat Hospital recognize they are dealing with acute radiation syndrome at doses beyond local treatment capacity. Arrangements are made to evacuate the most severely affected to Hospital No. 6 in Moscow, a specialized facility with experience treating radiation injuries from prior Soviet nuclear and military incidents. Aircraft transport begins. By evening, dozens of patients are in Moscow undergoing detailed evaluation. Acute radiation syndrome progresses in phases. The prodromal phase, nausea, vomiting, and malaise, begins within hours at high doses. A latent phase may follow, where symptoms temporarily improve, misleading patients and physicians into thinking recovery is underway. Then the manifest illness phase begins. Bone marrow failure, gastrointestinal damage, skin breakdown, and susceptibility to infection. At doses above 6 Gray, bone marrow produces insufficient blood cells. Without transplant, patients succumb to infection or bleeding within weeks. Medical teams in Moscow document dose estimates based on symptom onset, lymphocyte kinetics, and chromosomal aberrations in blood cells. Doses for the most severely affected firefighters and operators range from 4 Gray to over 10 Gray. 13 bone marrow transplants are attempted, mostly from family members, but rejection and complications limit success. Of 134 individuals ultimately diagnosed with ARS, approximately 106 are hospitalized. 28 die within 4 months. Most deaths occur among those receiving doses above 6 Gray, primarily firefighters who worked on roofs near the open core, and plant operators who were inside the reactor hall attempting to control systems in the immediate aftermath. The clinical data from Chernobyl becomes one of the most detailed datasets on high-dose radiation exposure in medical literature. Studies document dose-response relationships, chromosomal damage, skin injury patterns, and the limited efficacy of various interventions at extreme doses. Later analyses, published in peer-reviewed journals and compiled by UNSCEAR, provide dose distributions and health outcomes for responders and the broader exposed population. The findings confirm that prompt high-dose exposures above 6 to 7 Gray have grim prognoses despite aggressive medical care. For the families and colleagues of the responders, the first days are marked by confusion and fear. Pravik, Kibanok, Ignatenko, and others entered the hospital as firefighters injured in the line of duty. Within weeks, they are among the first civilian fatalities of a nuclear disaster. Their sacrifice, responding to what they believed was a conventional fire, becomes emblematic of Chernobyl's human cost. Monuments and memorials in Ukraine and Russia later honor these individuals by name, recognizing that they worked under misinformation and faced hazards they were never trained to confront. By the end of April, as evacuations expand and international attention grows, the medical consequences for first responders are becoming clear. The invisible doses delivered in the first hours have already determined outcomes for some. Treatment can mitigate suffering and delay progression, but cannot reverse the fundamental cellular damage caused by whole-body exposures in the range of 6 to 16 Gray. The numbers, sieverts, Gray, lymphocyte counts, quantify what survivors and medical staff experience as profound human tragedy. 27 April, 1400 hours. Loudspeakers mounted on buildings throughout Pripyat broadcast an announcement. An accident has occurred at the Chernobyl nuclear power plant. In connection with this, it is necessary to temporarily evacuate residents. Prepare documents, essential items, and a small amount of food for 3 days. Buses will arrive shortly. The announcement is calm, bureaucratic, no mention of radiation, no explanation of the reactor's destruction. Residents are told evacuation is temporary and precautionary. Preparations are orderly. People pack small bags, close windows, leave keys with neighbors. Many assume they will return within days. Outside, a convoy of approximately 1,200 buses is assembling. The Soviet civil defense system mobilizes on short notice. Drivers are brought from across Ukraine. Police and civil defense personnel coordinate the operation. Routes are planned. Pripyat's 49,000 residents are to be evacuated in a single operation lasting approximately 3 hours. From a public health perspective, the decision to evacuate balances incomplete information, logistical constraints, and political considerations. The reactor exploded 36 hours earlier. Radiation surveys of Pripyat show elevated levels, readings in the range of tens to hundreds of microsieverts per hour in certain locations, far above background. Contamination is heterogeneous. Some streets show moderate levels, others much higher, depending on wind patterns and particulate deposition. Iodine-131, with an 8-day half-life, is a primary concern. Inhalation and ingestion of I-131 concentrate dose in the thyroid gland, particularly in children. Dose reconstruction for Pripyat residents uses monitoring data, meteorological records, and models of contaminant dispersion. Average effective doses to evacuees are estimated at 10 to 30 millisieverts, roughly equivalent to several years of natural background. Some individuals, especially children who consumed contaminated milk before evacuation, received thyroid doses in the range of hundreds of millisieverts to a few sieverts. These doses are significant for cancer risk, but not acutely life-threatening. The 36-hour delay before evacuation is later scrutinized. Had evacuation occurred within the first few hours, inhalation and ingestion exposures would have been lower. Delaying allows time to organize a large-scale evacuation safely, but results in higher cumulative doses. Soviet decision-making reflects tension between acting on incomplete data and appearing to overreact. The political context, desire to avoid panic, minimize international attention, and maintain the image of control, affects the timeline. Residents board buses in an organized flow. Pripyat empties street by street. Families carry luggage, hold children. Pets are left behind. No provision for animals. The journey relocates most evacuees to temporary housing in nearby towns and cities outside the developing exclusion zone. Pripyat's buildings, schools and apartments remain standing but unoccupied. Over subsequent weeks, as contamination surveys continue and the understanding of fallout patterns improves, additional villages are evacuated. The exclusion zone expands from a 10-kilometer radius to 30 kilometers and eventually encompasses areas based on soil contamination levels rather than simple distance. Pripyat never reopens. The city, built to house nuclear workers and their families, becomes a symbol of the accident's permanence. Decades later, vegetation reclaims streets, buildings decay. Tourism and research access is controlled. The evacuation, framed on 27 April as temporary, becomes permanent for the vast majority of residents. For children exposed in the first days, the long-term consequence is elevated thyroid cancer incidence. Studies tracking evacuee populations, particularly those under 18 in 1986, document approximately 20,000 cases of thyroid cancer attributable to I-131 exposure over subsequent decades. Most cases are successfully treated. Fewer than 20 deaths are directly attributed. The health impact, while serious and affecting thousands, is bounded and statistically measurable, contrasting with early fears of far more widespread effects. The evacuation of Pripyat marks the transition from localized industrial accident to regional disaster. 49,000 lives are displaced. A city is abandoned. The geographic footprint of Chernobyl is no longer measured in meters around the reactor, but in kilometers across the landscape. 28 April 1986, Forsmark Nuclear Power Plant, Sweden. Routine personnel monitoring detects unexpected radioactive contamination on workers entering the facility. Radiation protection staff investigate. Initial assumption, a leak within Forsmark itself. Comprehensive surveys of the plant find no abnormalities. Ambient monitors outside the facility, however, show elevated levels. Contamination is external. Air samples are collected and analyzed using gamma spectrometry. Results show iodine-131, cesium-137, cesium-134, and other isotopes characteristic of nuclear fission. The isotope ratios and absence of certain activation products rule out a weapons test. The source is a reactor accident, and the material is fresh, released within days. Meteorological back trajectory analysis, tracing air mass movements, points toward the Western Soviet Union. Sweden is not alone. Over the next hours and days, monitoring stations in Finland, Denmark, Norway, and other European countries report similar findings. Atmospheric dispersion models, using wind data, reconstruct plume trajectories. All paths converge on a region in northern Ukraine. The Soviet Union has not issued any public statement or international notification. Swedish authorities contact Soviet officials through diplomatic channels. Initial responses are evasive. On 28 April, under mounting evidence and international pressure, a terse Soviet announcement acknowledges an accident at the Chernobyl nuclear power plant and states that measures are being taken. Details are sparse. International news agencies begin reporting the incident. Satellite imagery, though limited by 1986 resolution, shows damage to the Unit 4 building. For Western nuclear operators and regulators, Forsmark's detection transforms Chernobyl from a rumoured incident into a confirmed major release. The question becomes, how much material was released, where did it go, and what are the cross-border consequences? Over subsequent days, a picture emerges from airborne monitoring, ground surveys, and environmental sampling across Europe. Radioiodine is detected in milk in multiple countries. Cesium-137 deposition varies widely, influenced by rainfall and local topography. Some regions in Scandinavia, Central Europe, and the Alps receive significant fallout. Others, despite proximity, receive little due to wind patterns. The accident's environmental signature is heterogeneous and widespread. Estimated total release from Chernobyl is approximately 5 to 6 exabecquerels of radioactive material, including volatile fission products and some fuel particles. This is roughly 400 times the iodine-131 release from the 3 Mile Island accident in 1979, though still a small fraction of the reactor's total inventory. Release continues for roughly 10 days as fires in the graphite core persist and efforts to smother the core with materials dropped from helicopters proceed. International bodies, including the International Atomic Energy Agency, convene meetings to assess the situation. The Soviet Union eventually provides more detailed information, culminating in an August 1986 report to the IAEA, summarizing the accident's cause, chronology, and response. The report forms the basis for initial international understanding, though it emphasizes operator error and downplays design deficiencies, a framing later revised in INSAG 7 after further analysis. For European populations, the practical consequences include restrictions on food consumption, particularly fresh vegetables, milk and meat from areas with elevated cesium deposition. Agricultural products are tested, limits are imposed, economic impacts affect farmers and food industries. Public concern is high, fueled by incomplete information and fear of invisible contamination. Governments issue guidance, some conservative, some reassuring, depending on national context and measured contamination levels. Long-term environmental monitoring shows that cesium-137, with a 30-year half-life, persists in soils and ecosystems. Certain mushrooms, berries, and game animals in affected regions continue to show measurable contamination decades later, though typically below levels that pose significant health risk if consumed in normal quantities. The detection in Sweden and subsequent international fallout ensure that Chernobyl cannot remain a Soviet internal matter. It becomes a global event, prompting changes in international reporting protocols, reactor safety standards, and cross-border cooperation on nuclear emergencies. Forsmark's alarms, triggered by particles that travelled over 1,000 kilometres, mark the moment Chernobyl's consequences escape the control of any single nation's information management. May 1986 onward, Chernobyl site and the expanding exclusion zone. A liquidator's dosimeter alarm sounds. Time on the roof, 40 seconds. Total accumulated dose for the shift, the equivalent of several months' natural background, delivered in less than a minute. The Soviet response to an open reactor core with no containment requires improvisation at massive scale. Initial efforts focus on extinguishing fires and preventing further release. Helicopters drop materials, sand, clay, boron, lead, onto the exposed core in an attempt to smother reactions and absorb radiation. Pilots fly through contaminated air. Many sorties deliver material, though the effectiveness is debated. Some materials may have initially increased core temperature before achieving smothering. Longer-term stabilization requires constructing a barrier around Unit 4. The structure, later known as the sarcophagus, must enclose the destroyed reactor, limit further release, and allow some degree of monitoring and access for future decommissioning. Engineering challenges are immense. Construction occurs in a high radiation environment. Remote equipment, brought to the site, often malfunctions in the intense fields. Human labor is required for critical tasks. Liquidators, a term for the recovery operation workers, are mobilized from Soviet military reserves, civil defense, and volunteer units. Estimates suggest roughly 500,000 to 600,000 individuals participate in cleanup and stabilization efforts over multiple years. Dose limits are set. Initially, 25 Röntgens, approximately 250 millisieverts, for the operation. Some workers, especially in the first months, receive doses near or exceeding these limits. Others, working in less contaminated areas or later in the recovery process, receive much lower doses. Specific tasks include decontamination of buildings, removal of contaminated soil and vegetation, clearing debris from roofs, and constructing the sarcophagus. Roof debris removal becomes one of the most challenging assignments. Graphite blocks and fuel fragments litter the roof of the turbine hall and adjacent structures. Radiation fields near some debris pieces exceed 1 Röntgen per second, hundreds of Gray per hour. Exposure times must be minimized. Liquidators work in short shifts, run to the debris, shovel material into a container, or push it off the roof, run back. Some shifts measure 40 to 90 seconds of actual work before dose limits are reached. The sarcophagus itself requires roughly 400,000 cubic meters of concrete and 7,300 tons of metal structures. Design and construction proceed iteratively. Sections are prefabricated off-site, transported and assembled in place. The structure is not airtight, it is designed to allow ventilation and prevent pressure buildup. Over time, the sarcophagus experiences degradation. Water infiltration, structural settling, and corrosion threaten integrity. Concerns about collapse motivate a long-term project to replace it. Dose records for liquidators are incomplete and vary widely in quality. UN SCIR, reviewing available data, estimates that average effective doses for recovery operation workers were approximately 120 millisieverts. This is roughly 40 times annual natural background, delivered over months or years of work. A subset of workers received higher doses, particularly those involved in the first months. Long-term health studies of liquidator cohorts show increased rates of certain cancers, though attributing individual cases to radiation exposure versus other factors remains complex. The sarcophagus stabilizes the situation, but is never considered a permanent solution. By the 2010s, international cooperation funds construction of the new safe confinement, a massive arch-shaped structure built adjacent to Unit 4 and slid into position over the old sarcophagus. The NSC, completed in 2016, provides a weatherproof barrier and allows for future dismantling work inside. The project is one of the largest movable structures ever built, underscoring the decades-long engineering and financial commitment required to manage Chernobyl's legacy. From the destroyed reactor on 26 April 1986 to the completion of the new safe confinement 30 years later, Chernobyl remains an active site of industrial effort, risk management, and technical innovation. The human cost, measured in liquidator doses, health outcomes, and disrupted lives, is immense. The technological response, culminating in a structure designed to last a century, reflects the scale of the challenge created in less than a minute. Moscow and Vienna, 1987 and beyond. In July 1987, a Soviet court delivers verdicts in the Chernobyl trial. Viktor Brukhanov, plant director, Nikolai Fomin, chief engineer, Anatoly Dyatlov, deputy chief engineer, and 3 others receive sentences ranging from 10 years in labor camps to lesser terms. The charges focus on safety regulation violations and negligent management. The trial narrative emphasizes operator error and procedural non-compliance. Design flaws receive less attention. The court holds individuals responsible for the accident. International analysis follows a different trajectory. The IAEA convenes expert meetings. The Soviet Union submits a detailed technical report in August 1986, which becomes the basis for an initial International Nuclear Safety Advisory Group assessment, known as INSAG-1. This first report largely accepts the Soviet framing. Operator actions, in violation of procedures, caused the accident. Design weaknesses are mentioned but not emphasized. Over subsequent years, as more data becomes available and independent analyses proceed, the narrative shifts. In 1992, the IAEA publishes INSAG-7, a revised assessment. INSAG-7 reweights causation. While acknowledging that operators violated procedures, the report emphasizes that RBMK design deficiencies created the conditions where such violations could lead to catastrophe. The positive void coefficient control rod design with graphite displacers and inadequate information provided to operators about reactor behavior in off-normal conditions are highlighted as fundamental design flaws. The report notes that operators were inadequately trained on the risks of low-power, low ORM operation. Regulatory oversight is critiqued as insufficient. In SAG-7's conclusion, Chernobyl was a system failure, not merely operator error. Design, training, procedures, and regulatory culture all contributed. This reframing influences reactor safety philosophy. Designers recognize that reactors must be forgiving of human mistakes, not reliant on perfect operator performance. Defense in depth must include passive features and automatic protections that function even when procedures are violated. In the Soviet Union and successor states, RBMK reactors undergo extensive modifications. The positive void coefficient is reduced by enriching fuel and adding fixed absorbers. Control rods are redesigned to eliminate the positive scram effect. Minimum ORM limits are made more conservative. Operator training is revised. Additional automatic scram signals are installed. These changes implemented across the remaining RBMK units reduce the likelihood of a Chernobyl-type accident. Several RBMK plants continue operating into the 2010s, with some still active as of the present day, under much modified designs and procedures. Globally, Chernobyl reshapes nuclear safety practices. Probabilistic safety assessment, analyzing low-probability, high-consequence scenarios, becomes standard. Severe accident management procedures are developed. Reactor vendors reassess containment designs, operator interfaces, and passive safety features. Regulatory independence is emphasized. Regulators must be separate from operators and promoters of nuclear energy. International reporting frameworks improve, leading to conventions on early notification and mutual assistance in nuclear emergencies. The International Nuclear and Radiological Event Scale, INES, is formalized to provide a common language for describing accident severity. Long-term health impacts, extensively studied, present a complex picture. Among the 134 confirmed ARS cases, 28 die within months. An additional 19 deaths among recovery workers and exposed populations are attributed to radiation over subsequent years, bringing direct fatalities to fewer than 50. Thyroid cancer incidence among those exposed as children increases significantly, approximately 20,000 cases over 3 decades, predominantly successfully treated. Ewan Sear, reviewing the epidemiological data, concludes that the vast majority of the population need not live in fear of serious health consequences from the Chernobyl accident, while acknowledging the real harm to those most heavily exposed and the significant psychological and social impacts on affected communities. The Chernobyl Forum, a consortium of UN and other international agencies, estimates that approximately 4,000 additional cancer deaths may eventually occur among the highest exposed populations, though attributing individual late cancers to radiation versus other factors remains statistically uncertain. These projections, controversial and debated, reflect the difficulty of detecting small increases in cancer rates against high baseline incidence. Chernobyl becomes more than a technical case study. It is a reference point in public debates on nuclear risk, a symbol invoked in energy policy discussions, and a historical marker for technological hubris and systemic failure. The exclusion zone, covering approximately 2,600 square kilometers, remains largely uninhabited, serving as an unintended nature reserve and a site of ongoing research, tourism, and memory. The accident reshaped reactor designs, regulatory practices, and international cooperation. One low-power safety test at an RBMK led to the permanent evacuation of more than 300,000 people, deployment of roughly 500,000 recovery workers, and fundamental changes across every major nuclear program, demonstrating how a single, poorly bounded experiment conducted under conditions never fully analyzed can redefine global understanding of acceptable reactor risk.